Hi students, now we are in module 1. The module 1 is all about air standard cycles. Air standard cycles talk about all the 5 different cycles which come under the automobiles that are internal combustion engine. So what are those 5 cycles? The one is um, Otto cycle, next one is diesel cycle, next one is dual cycle, next Stirling cycle, and next one is Carnot cycle. So these 5 cycles are there in air standard cycles. Now, in my previous videos, I have explained about the efficiency of Otto cycle and efficiency of diesel cycle. Now, in this video, I am going to talk about the efficiency of dual cycle. So, if you want to have a clarification of that two different cycles efficiencies, you can check in my previous slides. So, in this video, I am going to talk about the efficiency of dual cycle. So this is the PV and TS diagram of dual cycle for any cycle for that matter. So you should understand how to draw the PV and pressure, volume and temperature entropy diagrams. If you understand these two diagrams, then that efficiency of any cycle will be easy for you. Okay, so how to draw this dual cycle? I'll just explain it to you. See the 1 to 2 process, 2 to 3. If you look at that Otto cycle, you will find only 1 to 2 process, and then 2 to 3 process will be there, and then 3 to 4. So it will be that there is no horizontal line, so it will be come back to this fifth position, and then it will be come back to the first position. So if you look at the diesel cycle, so there will be constant pressure. When you talk about Otto cycle, it is a constant volume. When you talk about diesel cycle, it is a constant pressure. Now if you combine both constant pressure and constant volume together, that is nothing but dual cycle. So the rest of the things what we have done in Otto cycle, what we have done in diesel cycle will be the same for dual cycle. But only the difference is the combination of these two will be the efficiency of dual cycle. So we will see in detail. So this is the PV and TS diagram, and let us understand the different processes. So 1 to 2 process is isentropic compression, as we have seen earlier, and 2 to 3 process. See, 2 to 3 process in between, so it is showing as X. 2 to x and x to 3. So what is all about this 2 to x and x to 3? See, 2 to 3 process in between, there will be combustion takes place. That is what heat addition process. So that is why it is talking about constant volume heat addition. And then x to 3, constant pressure heat addition. So that means if you look at that picture diagram, PV diagram, 2 to 3 will be the constant volume heat addition, and 3 to 4 will be the constant pressure heat addition. That means in dual cycle there will be two different heat additions will be there. One is constant volume heat addition, another one is constant pressure heat addition. In diagram we can see 2 to 3 is constant volume and 3 to 4 is constant pressure. That is only the difference here in dual cycle, and rest are the same. Like 4 to 5 process is isentropic expansion, that is adiabatic expansion or isentropic expansion. Again 5 to 1 is constant volume heat rejection. Okay, the same thing if you look at the TS diagram. So 1 to 2 process is adiabatic process, compression process, and 2 to 3 process is constant volume, and 3 to 4 is constant pressure, and both are heat addition. That is why the arrow mark is showing like heat is coming inside the system, that is heat added or Q inlet heat addition. And 4 to 5 is isentropic expansion, and 4 to 1 here 4 to in figure 5 to 1 it is showing as arrow mark is coming outside. That is nothing but heat rejection takes place over there, heat rejection during constant volume process. So what we can understand in these diagrams is like 2 to 3 process and 3 to 4 is both are heat addition process, and 5 to 1 process is heat rejection process. But we have to apply constant volume, constant pressure, those formulas only. Okay, so this is the PV and TS diagram. So next we will see the formulae. So what is the heat rejection? Heat rejection is where it happens actually between 5 to 1 process. That is why we have to write, it is a constant volume of course. So that is why we have to write QR is equal to MCV T5 minus T1. So this is how we have to write the equation for heat rejection. Why CV? Because constant volume. Why T5 minus T1? Because this happens between fifth state and first state, 5 to 1. So that is why T5 minus T1. Next, coming to heat supplied. If you look at the diagram, there are two heat additions are there. One is between 2 to 3, another one is 3 to 4. So these two things we have to write. How to write this? So 2 to 3 processes constant volume. That's why QS is equal to MCV T3 minus T2. 3 to 4 is constant pressure. That is why MCP T4 minus T3. So now we got heat rejection and heat supplied QS. Both are there. With this, we can write the efficiency formula for dual cycle. Now let us write the efficiency formula. So what is efficiency? Any efficiency output by input. What is output here? Net work done. What is input here? Heat supplied. So net work done is equal to QS minus QR, which is nothing but heat supplied minus heat rejected will be the net work done. Same thing we have, it is written in the numerator. Heat supplied, what is heat supplied? MCV T3 minus T2 plus MCP T4 minus T3. This is heat supplied, okay? Minus, what is heat rejection formula? MCV T5 minus T1, okay? Everything comes under numerator. Now coming to the denominator, so what is heat rejection? So same thing. So MCV, so net work done divided by heat supplied, not heat rejection, heat supplied. Heat supplied means again we have to write MCV T3 minus T2 plus MCP T4 minus T3. Alright. Now coming to the efficiency of dual cycle. Now what we have to do is, whatever the things are in common, we have to take it outside. So to simplify the equation, we have to do like this. So if you take what is in common, if you take it outside and cancel the both numerator and denominator, what is leftovers? Leftovers will be 1 minus T5 minus T1 divided by T3 minus T2 plus gamma into T4 minus T3. Now what is gamma here? Cp by Cv is equal to gamma. Right? What is gamma stands for? It's a adiabatic index. Adiabatic index is nothing but gamma. So T5 minus, so gamma comes here in the denominator. So next equation. Now, in the previous slide, if you look at it, so everything in terms of temperature, right? So in the previous slide, if you look at it, so everything in terms of temperatures like T5, T1, T3, T2, T4, T3. So what we have to do is, we have to convert everything into one particular temperatures, like all uniform temperatures, so that it is very easy for us to cancel it. So for that reason, in the next slide, what I am going to do is, so T5 by T4 it can be written as V4 by V5 whole to the power of gamma minus 1. This is a temperature and volume equation, gas equation. So in that way, T5 can be written as T4 into V4 by V5 into to the power of gamma minus 1. Now this can be written as V4 by V5. It can be split into V4 by V3 into V3 by V1. So because V2 is equal to V3. You can verify in the diagram. So V2 volume 2 is equal to volume 3 because constant volume. If we substitute that, so finally you end up here T5 is equal to T4 into RC divided by R whole to the power of gamma minus 1, where RC is equal to compression ratio, right? Gamma is adiabatic index whole to the power of gamma minus 1. So finally, if you still further simplify, you will be ended with T5 is equal to T1 pressure ratio, compression ratio whole to the power of gamma. So this is the T5 equation. Now we can see clearly what are those. V1 by V2 is equal to compression ratio, P2 by P1 is P3 by P2 is equal to explosion ratio. We can call it as pressure ratio, right? Next V3 V4 by V3 is equal to rho. Rho means cutoff ratio, where fuel is cut off. right? So efficiency, if you write the efficiency in terms of that, so finally you will get the, so T5 already we got. Next T4 is equal to rho into alpha T1 r to the power of gamma minus 1, right? So we got T5, we got T3, so everything in terms of pressure ratio and compression ratio and then cutoff ratio. So what we are trying to do is all the temperature parameters we are converting into ratios. What kind of different ratio? Three different ratios are there: explosion ratio, cutoff ratio, and pressure ratio, right? So next, if you look at it, so finally, if you solve, if you simplify everything, if you put everything whatever we have found out here, so finally the dual efficiency is equal to 1 minus 1 divided by r to the power of gamma minus 1 into rp into rc whole to the power of gamma minus 1 divided by rp minus 1 plus gamma into rp into rc minus 1. See, in this, r is equal to compression ratio, and Rp is equal to pressure ratio, Rc is equal to cutoff ratio. You can write Rc, or you can write rho. In terms of compression ratio or cutoff ratio, you can write rho also. Like, so Rc, R into rho whole to the power of gamma minus 1 divided by R minus 1 plus gamma into R into rho minus 1. So you can, so different textbooks will follow the different notations, so you can follow anything whichever you like. So what is written, we can use the same expression as before to obtain the mean effective pressure. To obtain the mean effective pressure in terms of the cutoff and the pressure ratios, we have the following expression. So this is the dual efficiency of dual cycle. Thank you.